this is a video about trigonometric identities. We'll talk about the concept of what an identity is, and then we'll list the identities that we have so far, and we might even demonstrate a couple of them as we go along, ones we haven't demonstrated already. So the concept, if I have an equation like x squared equals 9, well, I can solve that and say, oh, well, x equals plus or minus 3. And this equation is true only if x is 3. If I say, oh, let's make x into, say, 7, right? 7 squared equals 9. Well, that doesn't work. That's just wrong, right? So this equation is true conditionally, on condition that x is chosen to be the right value, or maybe there's two values it could be. Then the equation is true. So this is called a conditional equation. Now, what if we have an equation like this? What if I have something like a squared minus b squared equals a minus b times a plus b? Now, if you try to solve this equation, you're going to run into some problems. If you pick numbers, it turns out it doesn't matter which numbers you pick. I'll sort of randomly, I'll pick, say, 9 and 7. Let's say 9 squared minus 7 squared, and that ought to be, if this equation is correct, 9 minus 7 times 9 plus 7, right? So I've got 81 minus 49, that ought to be 2 times 16, and sure enough, both of those are 32. That checks out. This equation is true for those chosen numbers, right? Well, it turns out it doesn't matter which numbers I pick. This equation is not true conditionally upon what numbers you pick. It's always true. It's just describing a feature of arithmetic and algebra, if you like. So this is called an identity equation. It's not meant to be solved. It's just describing a feature of the math involved. So a trigonometric identity is one in which it's an equation about trig equations. Well, rather, it's an equation about trig functions. It's a trig equation, and it's always true. It doesn't matter what theta is. It's always true. So starting with maybe the simplest ones are the quotient identities, which we've more or less seen already. So for example, tangent. Tangent, by definition, is y over x, right? If you think about features of a circle, the x, y, and r features of a circle and an angle in central position on that circle. That's y over x, but this is equivalent to sine theta over cosine theta. And if you want to think about y, clean that up a little bit. If you want to think about y, clean that up a little bit again. Okay. Think about y. Well, this is going to be y over r over x over r, and that reduces to y over x. So yeah, sure enough, tangent being defined as y over x is equivalent to sine theta over cosine theta. Cotangent is cosine theta over sine theta. And if you want to do the same analysis here, you can do that, and you can check that that's correct. But I'm mostly just listing identities. We'll get to proving them a little bit later. Next are the reciprocal identities. So, for example, secant theta, this is 1 over cosine theta, okay? Which I won't bother demonstrating, but you can check for yourself. If you replace secant with r over x, replace cosine with x over r, it checks out. That is correct. Cosecant theta, this is 1 over sine theta. And then cotangent theta, this is 1 over tangent theta. Okay. Next, we have the Pythagorean identities. Okay. So this is like basically these come from the Pythagorean theorem, essentially, is why they're called that. So a squared plus b squared equals c squared. Okay, so the first one is cosine squared theta plus sine squared theta equals 1. Okay. Now you can manipulate this equation. You could divide by cosine squared on both sides or divide by sine squared on both sides. I'll skip those details, but you can develop the other two from this one. So 1 plus tangent squared theta, this equals secant squared theta, and cotangent squared theta plus 1 equals cosecant squared theta. Okay, those are the three Pythagorean identities. And I'll point out that this one is one of the most important identities to know for trig identities. And if you learn nothing else from these videos, you memorize this equation. You're going to see it in Cal 1, Cal 2. If you're in engineering, you'll see it in EA1, EA2. It's going to show up a lot, so you need to know it. You need to memorize it. So next we have the even-odd identities. When we talked about the trig functions, we defined them. We talked about domain and range. We also talked in the graphs. We also talked about even and odd functions. So the even functions, or the even, I guess the identities that identify the even functions. First is cosine. Cosine of negative x is equal to cosine of x. The negative input doesn't affect the result, so cosine of 2 is the same as cosine of negative 2. Secant is also even. So secant of negative x equals secant of x. Okay? So those are the even functions. Now the odd identities, all the other trig functions are odd. So sine of negative x equals negative sine of x. Cosecant of negative x being the reciprocal of sine of negative x, that's also going to be negative cosecant of x, being the negative of the reciprocal of sine, right? If you check this out by replacing cosecant with 1 over sine, you get the same result. You find that the two sides are equal. Then tangent is also odd. So tangent of negative x equals negative tangent of x, and then cotangent of negative x is also equal to negative cotangent of x. So those are the even-odd identities. Next, we have identities based on the period of each trig function, which these you don't have to express as identities, although they are. I need to add a page here. A page. Well, oh, okay, that was just a display error. Okay, great. Okay, sorry about that. Little display error. Okay, so the period identities are basically utilizing the period of each function. So sine of x plus 2 pi, since 2 pi is the period, adding 2 pi inside doesn't affect the result. This is sine of x. Okay, and then the same for cosine, secant, cosecant. They have the same period as sine, so it's essentially the same thing. So cosine of x plus 2 pi, this is going to equal cosine of x. Secant of x plus 2 pi, this is secant of x. And then cosecant of x plus 2 pi, this is cosecant of x. Now tangent and cotangent don't have a period of 2 pi. They each have a period of pi. So tangent of x plus pi equals tangent of x, and cotangent of x plus pi equals cotangent of x. You know, for each trig function, if you add the period inside the function, you know, x plus whatever the period, that doesn't affect the value because the functions are periodic. The last ones on our list are the cofunction identities, and this is something that we haven't talked about much, maybe a little bit. Cofunction identities. So I want to talk about these a little bit, not just list them, but talk about them a little bit. So if I make a triangle, It needs to be a right triangle. Let's see if I can. There we go. Cool. Okay. So let's say I call this angle theta. I call this angle, say, phi. And then I'll say this side is A, this side is B, and this side is C. All right. Well, since this is a right triangle, that means that theta and phi add up to pi over 2. Really, let me back that up. Theta plus phi plus pi over 2, or 90 degrees. If you add up all three angles, right, add up the right angle along with those two, you get pi, or 180 degrees, right? So if I subtract pi over 2 on both sides, that means that theta plus phi is pi over 2, right? Pi minus half of pi leaves you with half of pi. So these are complementary angles. Complementary. Okay. So this is where cosine comes from, essentially. If I say sine of theta, right, based on my triangle, right, opposite over hypotenuse, that's going to be A over C, right? Now, if I say, what is cosine of phi? Well, that's going to be, focused on the angle phi. It's going to be adjacent over hypotenuse, which is also A over C. Okay, so they're equal. But phi, remember, phi plus theta equals pi over 2. So if I take this equation, let me change colors here quick. If I take this equation and I subtract theta on both sides, I'll get that phi equals pi over 2 minus theta. And I can substitute that in. So this equals cosine of pi over 2 minus theta. Right? Now, of course, these two are equal. A over C is A over C, of course. So that means that these two are equal. Sine theta is equal to cosine of pi over 2 minus theta. Okay? And there's some historical reasons, like the co in cosine comes from complementary. Cosine is complementary to sine in a sense. Maybe we'll have a video with more detail on that if anyone asks for it. We'll just leave it be for now. So my first cofunction identity that we need to have is sine of theta equals cosine of pi over 2 minus theta. And along with that, sort of a companion to it, is kind of the reverse statement. Cosine of theta equals sine of pi over 2 minus theta. Okay, they're basically saying the same thing because sine and cosine are cofunctions. But then the other functions in pairs do the same thing. So secant of theta, well, this equals cosecant of pi over 2 minus theta, and cosecant of theta equals secant of pi over 2 minus theta. Okay. Tangent theta, this equals cotangent of pi over 2 minus theta, and then cotangent of theta equals tangent of pi over 2 minus theta. So in other words, if you have one trig function, like sine, and you would like to have cosine, but you don't care what the input is, you can switch to cosine by placing, basically, oops, I'm at the highlighter, basically inserting pi over 2 minus in front of theta, you can switch to the cofunction. So I've basically listed them, but later on we'll need to do that. We'll need to switch from one trig function to the other, to its cofunction, by introducing a pi over 2 minus in front of the theta. And that's basically it for these topics. In later videos, we'll use these basic identities that we've kind of developed as we went along. The cofunction identities are new with this video, but previously these are ones we had gotten to earlier. So basically, that's the beginning of this section in the textbook, and I guess that's it. That's the video.